Yesterday morning we introduced the notion of a group. Okay, so if you weren't here, I hope maybe you managed to watch the recording of the lecture. Just very quickly reviewing it, this material is quite different to the other material that I've been discussing with you up to now. It's more similar to some of the linear algebra material like that. So a group in mathematics is what we refer to when we've got this situation outlined in definition 5.1. When we've got a set G of mathematically interesting objects. The set might be a set of some kind of number-like objects, might be a set of functions, a set of matrices, or a set of other kinds of things you might not have encountered yet. And on this set, there is what's called a binary operation. So the binary aspect of it means it takes two inputs. So binary operation takes an ordered pair, a first element and a second element, combines them together in some mathematical way to give you a third element of the same type. Okay? You're intimately familiar with some of these things. Just think of numbers and addition. Addition is a binary operation. It takes two numbers, you add them together, you get another number. Multiplication. Addition and multiplication of matrices. Addition and multiplication of functions. Composition of functions. So such binary operations are all over the place. Okay? Now so that's just a set with a binary operation. In order to be a group, the pair have to satisfy these four conditions. Now we discussed these yesterday. The operation has to be closed on the set, meaning the product. So when I say the product, I mean the result of the operation of the two elements. The product of every ordered pair of elements has to be in the set. Associativity means the binary operation satisfies this basic associativity law. So the two ways of evaluating a triple product ABC, they always come to the same value. Condition 3 says there exists a special element in the set called the identity, which when you take the product of the identity in any other element, it leaves the other elements unchanged. And lastly, the fourth property says that every element in the set, for all A and G, there exists A inverse in G. So there exists a special partner element to A, which may happen to be A itself, typically not though. So an inverse element for A, and the property that has is when you take the product of A and A inverse, you get the identity element. So this is a very common setup to see in various kinds of mathematical structures. And what we started doing was looking at examples. So yesterday we considered the integers under addition, which was a group, the integers under multiplication, which was not, the real numbers under multiplication, which was still not a group, because we had to exclude the number 0. But as soon as we excluded the number 0 from the real numbers, then what was left, the non-zero real numbers, did form a group under multiplication. Okay, and then we launched into looking at this very important example. One example of a whole family of groups, and this is called the Dihedral Group T3. This is the group of symmetries of a regular triangle, an equilateral triangle. We discussed how such a triangle has 6 basic kinds of symmetries. Symmetries of such a figure in the plane, these are transformations of the whole plane. Distance-preserving transformations. So not anything like stretching the plane in any way or projecting bits of the plane on top of each other's. Okay? Just distance-preserving transformations, which for our purposes now we can think of as just rotations and reflections. Rotations about a fixed point or reflections in a line. If you want to reflect the plane, you're going to reflect it in a line. Okay? The regular triangle has 6 basic reflections. The identity transformation, the transformation of the plane which does nothing, it sends every point to itself. That is a symmetry of the triangle because you'll still be left looking at the same triangle. If you rotate the triangle a third of a turn, anti-clockwise, say, just to be specific, a third of a turn about its center, you'll still be looking at the same triangle. If you rotate it 2/3 of a turn about its center, you'll still be looking at the same triangle again. You can turn it 3/3 of a full turn if you want to produce another rotation, but of course that's already listed there because that's the identity transformation. To rotate the whole plane by 3/3 of a full turn, meaning you're rotating it a full turn. Well, as a function, as a before and after kind of thing, that's the same as doing nothing to the plane, because every point is centered. So. And then there are 3 reflectional symmetries of the triangle through these 3 axes, which we drew across it. Each axis goes through a vertex in the midpoint of the opposite side. Okay? They all go through the center point of the equilateral triangle. So S1 is the transformation of reflecting the plane in that axis. S2 and S3. And that is all the symmetries that there are. Now the claim is that this set of symmetries, this set of 6 operations on the plane, these are functions on the plane, we said that they formed a group. So to make sense of that, you have to say, well, what's the operation? What's the binary operation played? Well, the natural operation to use here, the meaningful one, is that of composition. Okay? We've got functions of the plane to itself. So the natural way to combine those together to get another function of the same type is to compose them. Okay, and this is where we finished last time. We started completing this thing which is called a Cayley table, named after British mathematician Cayley. The Cayley table for the Dihedral Group T3. Okay, so the Cayley table is just a multiplication table for the group. Okay, I'm really sorry, but lecture theatres are designed so that everybody can hear each other very well. You can all hear me, but equally well, I can hear everybody chattering. It's reached quite a loud level, so just keep it down. But do, if you got any questions or queries, do, I would like to hear those. You're always welcome to interrupt and those things in the discussion. Okay? So, we were constructing a Cayley table for the group. The Cayley table, when the group only has a small number of elements, this might be a practical thing. Obviously, this is going to become less and less useful, maybe, as the number of elements grows. But for a group with 6 elements, it is reasonable to hope to construct the multiplication table. And this is going to show you all values of the group operation. Under this convention, whereby, so we got all the elements of the group as row headings, all the elements of the group as column headings. Okay? And the convention is that the entry in the intersection of row X and row Y, that shows the value X, the product of X with Y. We need that convention because this operation we're talking about, composition of functions, it's not a commutative operation. So we need to have agreement about is this X after Y or Y after X? Okay. Well, the convention is it's X after Y, and that's the one we're going to follow. Okay? It'd be perverse or odd to have it the other way around. Just like driving on the other side of the road. Okay? So we got this far. It was immediately we ran across the top row and down the first column, because those are all products involving the identity transformation. By definition, the identity transformation doesn't change it. Then we started to think about, well, what happens when you compose rotation 1 with rotation 1? Okay, rotation 1 was rotating a third of a full turn. So when you compose that with itself, you get R2, rotating 2/3 of a full turn. And we found as well, when you compose R2 after R1, this entry here, you get the identity. Because rotation 1 is rotating a third of a full turn. Rotation 2 rotates 2/3 of a full turn. So in total, you've rotated a whole turn, so that's the identity. In the same way, rotation R1 after R2 is going to give you the identity. And what about R2 after R2, this entry here? What's that going to do?
R1.
R1, yeah. So if you rotate it twice by 2/3 of a turn each time, means you're rotating it by 4/3 of a turn. That's the same as rotating it by 1/3. Okay, that's good. As expected, anytime you compose a rotation with another rotation, you again get a rotation. So this top left corner of the body of the cake table is all rotations. Remember, we consider the identity transformation, doing nothing, that's a kind of rotation. Rotation by no radians or 2 pi radians. It's certainly not a reflection. The identity transformation. So in the same way, the kind of thing we expect when we compose a rotation with the reflection is to get, again, a reflection. If you think about it for a minute, that's the expected behavior. When you reflect the plane, see, shapes in the plane have this property of being right-handed and left-handed. Okay, your two hands look kind of similar, but you can't bring them to agreement. If they're both facing the same way, you can't superimpose your two hands, because one has got one-handedness, the other one has got the other handedness. When you reflect the plane, everything reverses its handedness. So a right hand profile looking at you, when you reflect the plane, it becomes the profile or the shape of the left hand. Okay? So if you perform a reflection, you're switching the handedness of things. But if you then compose that with a rotation, follow that by rotation, well, rotations don't change the handedness of things. Rotations preserve the handedness of figures. So if you compose a reflection followed by a rotation, things will still be in reverse handedness. So that will be, the overall transformation will be a reflection, because it will be something that has reversed the handedness of figures. The technical term for handedness is chirality, C-H-I-R-A-L-I-T-Y. So if you want to impress people, talk about chirality. It's the geometric concept of handedness. So but the question remains then, well, what is R1 after S1? It's certainly not going to be S1 again, okay? Because if we perform S1, then that's S1. But if you then move things around by rotating them a bit, you're going to change it. So it won't be S1. So the only possible values for this position here are S2 and S3. It's not screamingly obvious which one it is, so we should probably demonstrate how to work it out. Okay? Now here's our starting triangle. Now, in order to make it easy to track what's happening, we can label the vertices. Might as well label them. Ooh, sorry, I'm not going to label them 1, 2, 3 because that's going to confuse with my S1, S2, S3. So I'll label them with ABC. If you looked at the diagram we drew yesterday, S1 was reflection of this axis. S1 was reflection of that axis. S2 was reflection of this axis. And S3 was reflection of that axis. R1 was rotation by 1/3 of a turn anti-clockwise. And R2 was rotation by 2/3 of a turn anti-clockwise, which you can also think of as R1 squared. So what happens to our starting triangle, ABC, if we first perform, so this we're looking at this entry here, R1 after S1. So if you first perform S1, it's a symmetry of the triangle, it's still the same triangle you're looking at. But what's happened to the vertices? Well, if we've reflected in S1, A is still where it is, but B and C have swapped positions. And we then perform R1. So we rotate it by 1/3 of a turn anti-clockwise. Of course, it's still the same triangle because it's a reflection, but that moves these three vertices around somewhat. So A goes up there, C goes there, B goes there. Okay, that's the composition of the two symmetries. But we've composed two symmetries, two transformations that leave the triangle unchanged. So the composition of them, the overall transformation, should still be a symmetry. So it must be one of our 6 symmetries that is this. We're expecting to see a reflection. What you do here is you look at the before and the after pictures, and you try and work out which reflection it is. And once you examine the positions of the vertices of the vertex labels, you'll see which symmetry it is. Okay, because label C is still in the same position as it was when it started, and A and B have swapped their positions. Okay, so this overall transformation is clearly S3. It's had exactly the same effect as applying S3 to the starting triangle. So the entry in our Cayley table, in this position here, R1 after S1, is S3. Everybody clear on that? Any queries? No, R is rotation. By 1/3 of a turn counterclockwise. Is everybody clear what's happened here in these 3 pictures? What I was doing, I was applying S1 and then R1. So that's the composition R1 after S1. So by tracking the positions of the vertex labels, I'm able to correctly identify the overall transformation that has been applied. Okay. And in principle, we've got to do that kind of thing to figure out all the other values. Except we can speed it up a little bit by starting to use some consequences of the group axioms. Once I know that this is S3, this allows me to deduce what R1 after S2 is. Remember, R1 after S, so I'm now looking at the next position to the right. R1 after S2 is certainly not going to be S2, because we're performing S2 and then doing something slightly different. So it's not going to leave things the same as just trying S2. So that means this has got to be S1 or S3. Remember that R1 after S1 gives S3. And you can use the fact that every element here is an inverse, and that things like associativity and that allows you to use these simple cancellation rules. We've already discovered that R1 after S1 is S3. It couldn't be the case then that R1 after S2 was also S3, because that would imply that R1 after S2 is equal to R1 after S1. And you can multiply both sides on the left by R1 inverse. It's a bit small. You could multiply both sides on the left by R1 inverse to then imply that S2 is equal to S3, which is a contradiction. Because S2 and S3 are different. So that contradiction means that R1 after S2 can't also be the value of S3. So that only leaves one option remaining, that R1 after S2 is S1, and then R1 after S3 has to be the one reflection left. Same reasons, which is going to be S2. But again, if you wanted to figure out explicitly, first principles, what these entries were, you could use a vertex tracking argument like this to apply each of the individual symmetries and then to correctly identify the composition. Okay. So R2 after S1 then has to be S2, R2 after S2 has to be S3, and R2 after S3 has to be S1. Anyone at all unclear about, or still needs any clarification about how those values? So I use some quick elimination arguments to figure out what all the others should be. But in principle, all those other positions can be worked out by applying this method. And then the options in the bottom left. So in the bottom left, we're again composing reflections and rotations, but in the opposite order. In the bottom left square, we're doing a reflection after a rotation. Whereas up here in the top right, we were doing a rotation after a reflection. So this entry here, we're faced with S1 after R1. Now, S1 after R1 is not going to be the same as R1 after S1. It's going to be the only other option. So that's going to be S2. So let me demonstrate that one again. So S1 after R1. So there's our starting triangle, ABC. You apply S1 to it. A stays where it is, and B and C swap. And you then apply R1 to it. Oh, sorry. I'm doing R1 first. Sorry, I'm just repeating the same thing I had before. Here's my starting triangle. I first rotate, and then perform S1. Remember, S1 is reflection in this axis here. So reflecting in this axis here to the triangle. So C remains where it is there, and A and B are swapped. So then overall, this composition is S1 after R1. And we can identify that by querying the positions of the vertex labels. See here, B is in its same position, and C and A have swapped. So that means this must be S2. Because S2 is reflection in that vertical axis. Okay? And that's the one that's been applied from the beginning to the end. Okay? So that argument here explains this value S2 here, in the position S1 after R1. S1 after R2 then has to be the remaining reflection, S3. S2 after R1 has to be S3 here. S2 after R2 is going to be S1. Then you're going to have S1 and S2 there. Now this just leaves the bottom right, where we're composing one reflection after another reflection. If you think back to the handedness argument, applying one reflection will turn a left-handed thing, right-handed thing into a left-handed thing. Then you perform the other reflection in some other axis, but it will swap it back. So everything will be back to its original handedness after you compose two reflections. So that means the overall result cannot be a reflection, okay, because things are back to their original handedness. So that means it must be a rotation. So any reflection after another, composed with another, has to be a rotation. Which exact ones it is, you might have to do another one of these vertex tracking arguments to figure it out. So let's try and work, well, we know those diagonal entries are going to be identical, because every reflection is self-inverse. When you apply a certain reflection in a certain axis, and then reapply it, reflect again in that very same axis, everything is going to be back where it started. So that explains why these diagonal entries here, SI after SI, it is still, all I can hear is loads of people chatting. I don't mind talking about maths, but I think it's a lot of people are just chatting. Thank you. It's just the sound travels equally well in both directions for everybody. Thank you. Okay, so what about this next position here, S1 after S2? Again, we can work this out in the same way. Okay, I'll block my page for a second. So try and work out what this entry here, which is going to be S1 after S2. Now you'll need to refer to precisely which axes S1 and S2 are. So you're expecting one of the rotations there. So what did everybody get? Which rotation did you obtain? Anybody? So you've got R1 down here. R2. R1. Any more?
R1.
You lost. R1. Yeah, so I think R1 is correct. Did you compose the other way around? Yeah, so you composed them. You did S1 first and then S2. Yeah. So that's correct. S1 after S2 after S1 will be the other way. R2. Yeah. Okay, well that's good because that's efficient. So this is R1 and that's R2. So this will be R2, R1, R2, and R2. So that's how the table is. So once you get to that position, you've got a complete overview of all of the products that are going on in T3. And in order to do a little bit of group theory here, if you do end up doing the final year group theory unit, the grand enterprise of group theory is being able to get a complete classification of all possible groups. Now, to fully state exactly what that means takes a bit of technical jargon and so on. But the basic kind of question is, well, if you think of other groups that might have 6 elements, this group has 6 elements. If you think of other 6, we imagine other 6-element groups. How many intrinsically different types of groups with 6 elements are there? Or will it be the case, say, that every other 6-element group you encounter will maybe just be a version of this one, where the elements might have different names, but maybe the structure in the table about how the elements combine, maybe that would be the same structure as this. Okay. Because these particular letters, after all, are completely meaningless. All the letters do are just standing for the mathematical objects. It may be that another 6-element group you construct might display exactly the same structure in its table, or it might have a different structure. Okay, so let's encounter some more examples. So another important class of examples are the modular arithmetic groups. So Zn plus this is the group of integers between 0, 1, 2, all the way up to n minus 1. And the operation here is addition modulo, I'm just using the usual addition sign, but it's a slightly different addition. It's addition modulo n. Meaning that you add the two integers in the usual way, but then if it's bigger than n, you divide it by n and just look at the small remainder that remains. Okay? So for example, we want to look at Z6. Okay? Z6 as a set just consists of the integers 0 through 5. So addition modulo n is where you add a plus b in the usual way, then divide by n. Divide by n and take the small positive remainder, non-negative remainder. R, which satisfies R, is between 0 and n minus 1. So if we look at the K table for Z6 under addition, so this will be quicker to work out than the table for D3, because we're basically just adding things. So a lot of you may have encountered addition modulo something before. So we're just adding all these numbers. So when you add 0 to something, it doesn't change, of course. You add 1 to something, it increases it by 1. And of course, 5 would increase to 6, but you can divide 6 by 6 and you get a remainder of 0. So the result of adding 1 and 5 modulo 6 is 0. Yeah. Same way you can add 2 to anything. If you add 2 to 4, you get 6, which modulo 6 is 0. If you add 2 to 5, you get 7, which modulo 6 is 1, because you can divide 7 by 6 and it leaves a small remainder of 1. You add 3 to everything. Same way, 0, 1, 2. You add 4 to everything. Only add 5 to everything. So this is a closed system, certainly closed, isn't it? Every time you add 2 integers modulo 6, you get one of the ones in the set, 0 through 5. It's going to be associative because fundamentally it's based on an operation, just plain addition of integers, which we know to be associative. There is an identity. The identity element is clearly 0 itself. You add 0 to anything, it leaves the other thing unchanged. And everything has an inverse. The inverse is minus the number interpreted modulo 6. So the inverse of 3 is itself, 3 plus 3 is 0. The inverse of 4 is 2, 4 plus 2 is 0. 2 plus 4 is also 0. This group also is abelian. It's also clearly a commutative group because if you look at the main diagonal, you see that it's completely symmetric across that main diagonal. Okay, that's because x plus y is the same as y plus x. Now the modular additive groups, they all basically look like this. The top row of the Cayley table will be 0 through n minus 1. And the next one will be that row shifted one place to the left. The next one down will be the row above it shifted one place to the left. As you can see, it always is here. Okay, because each time you're just adding, as you fill it out row by row, each new row you're just adding on a number one bigger than you did in the previous row. So that has the effect of shifting everything to one click to the left each time. And whatever additive group Zn plus you look at, its Cayley table will display that same structure. But a different group is, what about the operation of multiplication? You can also do multiplication modulo something. You can also multiply A and B modulo n, where we take the same way, where we take the small, meaning less than n, non-negative, meaning greater than or equal to 0, the small non-negative remainder after dividing A times B in the usual sense by n. Except that we need to modify the set Zn though in order to form this group, because there's a problem with inverses. What's the identity going to be for this operation, multiplication modulo n? Well, just as in regular multiplication, the identity is going to be the number 1. If you multiply anything by 1, it doesn't change. But, so that means the inverses are going to have to be other integers, and when you multiply them by the first one, it gives you 1 modulo n. So an integer a will only have an inverse, a multiplicative inverse, meaning an inverse with respect to this operation of multiplication modulo n. An integer a will only have a multiplicative inverse modulo n if GCD of a and n is equal to 1, where GCD equals the greatest common divisor. Greatest common integer divisor between the two numbers. In order to have an inverse, the two numbers have to be like that. Another way of saying this is that a and n are co-prime. Now, this kind of thing is something that we investigate in great detail in the number theory and cryptography unit in second year. We study this in great detail and look at all the consequences of it and how ultimately these concepts get applied in modern cryptography systems. But so Zn with the superscript multiplication sign, this stands for the integers in Zn, i.e. the integers between 0 and n minus 1, where GCD of a and n is 1. So in order to get another 6-element group to look at, we can look at Z9. Because if you look at the elements of Z9, they will be 1, 2, 4, 5, 7, and 8. Okay? There's no 3, or there's no 6, and there's no 0. Because the greatest common divisor of 0 and 9 is 9. Everything divides. 0 can be divided by any integer. It always goes in 0 times. 3, the greatest common divisor of 3 and 9 is 3. The greatest common divisor of 6 and 9 is 3. And we're only considering the things up to n minus 1. So the set, the underlying set for the group Zn, Z9 under multiplication modulo 9, this has 6 elements. So again, we can construct its Cayley table. Now this might be slightly harder because we're multiplying, so the numbers are going to get larger. But the entries in all these positions will be one of the numbers 1, 2, 4, 5, 7, 8. So you're multiplying together the two numbers. And if it's a large number, you're looking at the remainder after division by 9. Multiplying by 1 is easy, it doesn't change anything. Multiplying by 2 is relatively easy. Okay, 2 by 5 is 10, which is
greater than it.
Bigger than 9, so what am I going to put down in the position for 2 times 5? 1, yeah, because 1 is the remainder. 2 times 7 is 14. So I'm going to put down 2 times 7 modulo 9. 5, yeah. So you're always putting the remainder after division by 9. 2 times 8 is 16, so that leaves a remainder 7. 4 times 2 is 8, 4 times 4 is 16, leaves 7. 4 times 5 is 20, leaves 2. 4 times 7 is 28, leaves 1. 4 times 8 is 32, leaves whatever I haven't put down yet, 5. 27 is 5. So you keep going across here. 5 times 2 is 10, which is 1. 5 times 4 is 20, which is 2. 5 times 5 is 25, which is 7. 5 times 7 is 35, which is 8, isn't it? 5 times 8 is 40, which is 4, bigger than 36, so that's 4. 7 times 2 is 14, which is 5. All these other ones I should have got so far. 1, 8.
Oh, yeah.
7 times 7 is 49. 4, 2. Then the last row is easy because the last row will just be whichever number hasn't been mentioned in that column so far. So that should be a 7. 5, 4, 2,
1.
and 1. Thank you. Okay, multiplication is always a bit harder. But there's yet another 6-element group. Okay, yet another 6-element group. It's closed because every entry in the body of the table is one of the 6 elements. It's associative. It's based on an associative operation. The identity is 1, and everything has an inverse because in every row the number 1 does appear. We could ask ourselves the question: is okay. The kinds of questions that group theory attempts to answer, it's successful in answering lots of these types of questions, but as the groups become larger, these questions become harder and harder to decide and understand what the range of possible answers is. What we can ask ourselves as questions is are those two groups the same? Okay, now your instinct is to say no because there's a 7 in the bottom one and there's no 7 in the top. But group theory doesn't really care about the fact that that's a 7 and it's not a 7 up there. Group theory cares about the elements. Group theory cares about how the elements relate to each other and how the operation works in the group. So really what we're asking is the structure displayed in the top table, is that equivalent in some way to the structure displayed in the bottom table, or is there some evidence in between what's going on in the top and bottom that would mean the structures are different? So you kind of have to imagine all possible relabelings of the elements in the top using the labels from the group in the bottom to decide whether or not they're the same.
What is the first one? No. Because there's only 12 different ways to have it. And one is a triangle with one. And then the other is
Now, there is an answer to it. Both groups are what we call cyclic. I.e., generated by a single element. If I could just hold your attention for another couple of minutes. Both of the groups are generated by a single element. For the Z6 plus, it's easy to see that the elements are 0, 1, 1 plus 1, 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1, etc. And 1 generates every element. 0 times 1 is 0. 1 times 1 is 1. 1 plus 1 is 2. 1 plus 1 plus 1 is 3. Okay? So you can build every element, you can build every non-zero element, non-identity element out of the element 1. So these are the elements, these are the real elements 0, 1, 2, 3, 4, 5. But you can also do the same in Z9 under multiplication, although it's not immediately obvious. You have to search a bit for it. Well, you've got the identity 1, you've got the element 2, you've got 2 squared, 2 cubed, 2 to the power of 4, and 2 to the power of 5. Now, in the group Z9, these elements are 1, 2, 4. Well, 2 cubed is 2 by 4, which is still 8. 2 by 8 is 7. 2 by 7 is 5. 2 by 5 is 1 again. So what this reveals is that if you relabel the elements of one group with its corresponding label here, you'll discover that the two groups as groups are really the same. Okay? The top Cayley table, if it was the top Cayley table, the two Cayley tables, if you relabel everything in the Cayley table for Z6 by its corresponding element from Z9 here under this assignment, the Cayley table from Z6 transforms into the Cayley table for Z9. So really, group theory considers those two groups to be the same. So if those two groups are the same, what about our group D3? Should we consider that to be the same as these groups? Or is there something fundamentally different in the groupiness of D3 compared to Z9/Z6, which we now consider to be the same? Is there something quintessentially different that's going on in D3 that you can see in the table? Okay, in D3, well, the first thing is that D3 is not commutative. So that automatically says it's quite a different kind of group than the commutative groups Z6 and Z9. But this Cayley table is symmetric, or is not symmetric under reflection. But something a bit more convincing is, look, there are 3 elements in D3 here, which when you square them, you get the identity. So there are 3 elements in D3, such that when you square them, you get the identities. Whereas in Z9, there's only 1 non-identity element, 8, such that when you square it, you get the identity. Every other non-identity element, when you square it, you do not get the identity. Whereas in D3, there are 3 non-identity elements, such that when you square them, you get the identity. That's enough to show that it's a significantly different group than any of these two. Okay, I've overrun by a few minutes, so I better leave it there. Thanks for your attention. It's just a small taste of some of the issues that group theory brought us. We'll say more about this next week.
That's all.